public key cryptography. So, hello everyone. Today's topic will be elliptic curve cryptography for blockchains. So, I divided this talk into three parts. First, I will briefly mention what public key cryptography is. Then I will give the necessary algebraic background, like groups, rings, and fields. Then finally, we will talk about elliptic curve cryptography, which are used in blockchains mostly for signing, okay, for digital signatures. So let's start. The idea of public key cryptography is first introduced by Diffie and Hellman in 1976. It is based on using a trapdoor function f. So it takes an input p and produces an output c. So this is somewhat different than a one-way function. So let's recall what a one-way function is. In the one-way function, you can think about this as a hash function. When you have the input x, it is easy to input fx. So you obtain the output in an easy way. But it is hard to invert. Of course, when we say hard, it means that computationally infeasible. Okay. So when you are given an output y, you also know the function f. It should be hard for you to find. It should be computationally infeasible for you to find an x such that fx equals to y. So this is what we actually talk about when we were talking about cryptographic hash functions, right? Now, Diffie and Hellman introduced another function called trapdoor function. Idea is almost the same. So again, it is very easy to compute the output when you know the input. And it is hard to invert again without extra knowledge. But if you have an extra knowledge, which we call the trapdoor, it is easier for you to invert it. So this idea is used in public key cryptography, okay? So this is why we will be talking about public and private keys. So public keys will be distributed to anybody that you want to communicate with, but private key will be only in your possession. So in digital signatures, we will sign the messages with our private keys, and people with the public key can check our signature and verify them. Of course, this public keys, again, as I mentioned, will be a point on the elliptic curve when we are talking about bitcoins. So this is a very old work, but you know, Diffie-Hellman received an ACM Turing Award in 2015, which is actually a very late award. Unfortunately, they deserved it much earlier. But anyway, because today on the internet, almost the whole security depends on Diffie-Hellman key exchange, which is actually introduced in that paper in 1976. So they come up with the idea and they introduce Diffie-Hellman key exchange, but they don't produce an encryption algorithm. So they give the idea for such a function, but they don't produce such a function. And RSA actually one of the first examples for such an encryption algorithm. But we won't be using them much in this lecture. So public key cryptography actually solves a lot of problems. So main tasks can be divided as follows. Confidential message transmission. So we have encryption and decryption algorithms in public key cryptography like RSA or Al-Gamal. And public key cryptography solves the problem of authentication with using digital signatures. And this is actually what we are going to focus on this lecture, because as I mentioned before, people think that there is encryption in cryptocurrencies since there is the word crypto, but actually there is no encryption, okay? But we will be constantly using digital signatures, because once we want to transmit a digital asset from you to somebody else, you have to digitally sign it, right? So this is why we need digital signatures. A third problem that public key cryptography solves is the key exchange. And Diffie-Hellman is one of the best examples for this case. So this allows us to exchange the key of a symmetric key crypto system through an unsecure channel. So this is the good thing, because on the internet, for instance, if you want to do a commercial transfer, if you haven't visited that web page before, by using Diffie-Hellman, you can agree on a secret key and then continue communicating in an encrypted way. So in order to understand how these algorithms work and why they are secure, we have to talk a little bit about complexity of algorithms. So let's start with polynomial time algorithms. An algorithm to perform a computation is said to be polynomial time algorithm if there exists an integer d such that the number of bit operations required to perform the algorithm with a k-bit input is OKD. So here we are using the big O notation. So we call it a polynomial because it is the integer power of some number here, right? Some value here. So we consider polynomial time algorithms as fast because there are a lot slower algorithms like exponential time algorithms. So this means that actually if the input size of your algorithm increases, your complexity increases in a polynomial way. But if it is an exponential time algorithm, depending on the size of the input, your work is actually increased in an exponential, right? That is the idea. So an exponential time algorithm has an estimate of big O notation with e to the ck, where k is the total input length and c a constant. Of course, here we are using the Euler e number, but you can write there 2 or 3, it doesn't matter. So it is a number here, but kth power comes from the input size, okay? So this is why it increases exponentially. So you can see that the polynomial time algorithms are a lot faster than these when the input size is large. But so in public key cryptography, I already mentioned that, when I said the word hard, I tried to explain that it is computationally infeasible, right? Here, actually, that computationally infeasible part comes from. So if the solution of to break a cryptographic algorithm requires exponential time complexity, then we will say that it is computationally hard. But if you can come up with a polynomial time algorithm that breaks the system, then that crypto system will be broken regardless of how big the size is, because it will be again polynomial. And the question is that can there be polynomials? Can there be algorithms which are slower than polynomial time but faster than exponential time? So question is, can there be anything in the middle? And the answer is yes, and we call them sub-exponential time algorithms. Okay, before moving on, I have an example here. Let me see. Yes, before the sub-exponential time algorithms, let me give you an example for an exponential time algorithm. So I already mentioned that in RSA, we choose two prime numbers, P and Q. We multiply them, obtain the composite number N. Then we ask you to factorize this number, right? So question is, can you find the factorization of an integer N? So if you don't have a fast algorithm for this, what you can do is to do a brute force attack, like by trying every possible thing, right? So you have the number N. So if it is an odd number, then there's no need to check if it is divisible by 2. So you can try all integers in the range starting from 3 to square root of N. So what you do is as follows. First, you check if 3 divides N. If it doesn't, you check if 4 divides N. If it doesn't, you check 5 divides N. So you continue in this way until you come up with the divisor, right? You have to try everything until square root of N, because if there isn't any divisor of N between this range, there's no need to check the larger numbers, because it will mean that there will be 2 integers larger than square root of N that divides N. But once we multiply those both numbers, that will be larger than N, which is a contradiction. So all you need to try is integers starting from the range 3 to until square root of N. Okay, so you have to check if any of these numbers divide. And if you come up with any divisor, then you will divide that number, you divide N with that number, and then say that it divides it, and then you continue the algorithm, this time with that's N divided by that number. But if you cannot come with anything, this means that this is a prime number. So that is the idea. So the question is, if I do that, how many operations do I need to perform, right? So first look at how many bits this integer N actually consists of. So if you calculate logarithm to the base 2 of N, the K actually means how many bits this number is consist of. So when I say a 200 bit integer, actually this is what I mean. So when you take the log 2 of that number, it will be 200, okay? So we say that this number N is a k-bit integer. Okay, so we know the K. So input size is k-bit, right? So what I do is to perform trials, which consist of maybe approximately square root of N trials. Each trial means that I check if this number divides N. So in each time I have to perform if n is divisible by that number. Okay, so this is the number of trials, 2 to the k over 2, right? So this is the number of operations I'm going to perform, right? So the question is, how many bit operations I need to perform a division? So I'm not going to show or prove you how it is, but you can probably see a very good example from Koblit's book. But the main idea is that division of a k-bit integer with a k over 2-bit integer. I say k over 2 because we are considering numbers less than or equal to square root of n. If k is m, if n is k-bit, then square root of n is k over 2-bit, right? So division of a k-bit integer with a k over 2-bit integer is of O k square. So it is a polynomial time algorithm when you perform a division. So you might see that where this 2 disappeared, actually you can write k squared over 2, but in the big O notation we don't care much about the constants. So this is why it is O k square. So for a single division, I perform this many operations. I'm going to perform this many divisions. So for the big O notation, this trial division algorithm actually has a complexity of 2 to the k over 2 times k square. So this part, k square, is actually dominated by 2 to the k. So this is why it is an exponential time algorithm. Okay, so if you try to find the divisor of a number, and in this way, when the size of n increases, your complexity increases exponentially. So this way, actually, you wouldn't be able to find divisors of large integers. So that is the idea. So the question is, can you come up with a better algorithm? The answer is yes. Actually, you can also make it faster by, instead of trying every number here, actually, all you need to do is to check every prime number between 3 to square root of n. But it will be still exponential time algorithm. So question is, can you come up with better algorithms? And the answer is yes. In the literature, we have index calculus algorithms that actually solves this factorization problem in a faster way. And they are sub-exponential time algorithms. So this is why we are going to talk about sub-exponential time algorithms. So the definition is somewhat looks strange. So we say that L gamma C, which equals to this big O notation, e to the ck to the power gamma times ln k to the power 1 minus gamma, where gamma is a value between 0 and 1, and c is something greater than 0. So if k is the input size of an algorithm, and if the estimate of the time cost of the algorithm is L gamma C with gamma between 0 and 1, the algorithm is called a sub-exponential time algorithm. So in order to understand why there is such a definition, let's see what happens when gamma is 0 and when gamma is 1. So it will actually tell us why there is such a definition, okay? So let's look at when gamma is 1. So you put gamma equals to 1 here. And if you put gamma equals to 1 here, 1 minus 1 is 0, so this part cancels out. So you end up with e to the ck, which is actually the exponential time algorithm. But if you choose gamma equals to 0, this k to the 0 is 1, so it goes out. And if you calculate e to the power ln to the k, so recall that from maybe high school, when you're performing logarithm, here ln means it is to the base e. So e to the ln actually cancels out, and this k comes to the front. So this is why you end up with k to the power c. Okay, so it becomes polynomial time. So when gamma is 0, it is polynomial time. When gamma is 1, it is exponential. So when gamma is something small, this means that the algorithm a lot faster, but slower than polynomial time. And if it is very large, the algorithm is slow, but it is still faster than exponential time algorithm. So this is the whole idea. And I'm mentioning this because there are sub-exponential time algorithms to solve factorization. This is why actually we are going to talk about, when we talk about key sizes, when you talk about elliptic curve cryptography, we say that the key size is like 256 bits. But when we talk about RSA, we talk about modulus n, which is the result from the multiplication of p and q. We talk about 3000 bit integers, right? So this is why that the number is larger than 256, because you have sub-exponential time algorithms to solve factorization. But since this is the case, in the Bitcoin, we always use algorithms that uses elliptic curve cryptography, so that there are no sub-exponential time algorithms to solve discrete logarithm problem there. So this is one of the reasons why we are going to talk about elliptic curve cryptography. Okay, and let's give a few more definitions. We actually define two types of problems. One of them decision, and the other one is a search problem. A decision problem is a problem whose solution or the output is yes or no. And the search problem is actually a problem whose solution can be more than yes or no. So let me give you an example. This is a search problem. Given n, factorize n. So as you can see, the output is not yes or no. You try to find the factors of this number. And the decision problem is somewhat similar. And here I give you the same n, but this time I ask you if it is prime or not. So here you can answer as yes or no. And you might think that these problems are identical. But one way it is identical, for instance, if you solve the first problem, you factorize n. If you find its factors, then you can answer this decision problem, because this time you know if it is prime or not. But the question is the reverse the same? So this means that, can I decide if a number is prime without finding its factors? And the answer is actually yes. The decision problem is a lot easier than the search problem. So this is why actually the RSA algorithm works, because we say that n is hard to factorize, right? It is a huge number, so we say that the search problem is hard. But when I start the algorithm, I tell you to choose two prime numbers and multiply them. So how can you choose big prime numbers if it is hard to decide if it is prime or not, right? But this is why this actually works, because the decision problem is easier than the search problem. Okay, this is why RSA works actually. Okay, let me give you a few examples of problems. Integer factorization search problem is one of them. The problem of finding a non-trivial factor m of an integer n, or else determine that n is prime. So there are sub-exponential time algorithms to solve this. Traveling salesman search problem is another famous problem. The task of finding the shortest or cheapest route that starts from a city A, passes through all cities on the salesman list, and return to A. So this is considered as an MP problem. So there is no polynomial time algorithm to solve every instance of this problem. Okay, so it is somewhat hard. And tree coloring search problem is also another example. So from graph theory, actually, we can prove that, consider any world map, regardless of which cities have borders with which cities. You can only use 4 colors so that none of the neighbors have the same color, okay? But the question is, can you also do it with 3 colors? Sometimes you can and sometimes you cannot. So this kind of a search problem is hard. The task of coloring vertices of a given map or graph with just 3 colors, such that no 2 neighboring regions vertices have the same color. So these are somewhat hard problems. But note that cryptographers generally don't consider much about, don't care much about MP problem, okay? Because computer scientists ask this question if P equals to MP or not. And people who don't work on the area of cryptography think that we rely the security of our algorithms on the fact that we are using MP hard problems, but most of the time we don't do that, okay? So actually we don't care much about the MPness or not. We actually care what is the fastest way to solve that problem. If it is a polynomial time algorithm, then it will be hard to use that crypto system in practice. If it's the best algorithm to solve it is exponential time, then we would be happy. If it is sub-exponential, like in the case of RSA, then we have to choose our key sizes so that current computational power of the world would not be enough to break that system.